All right. Hello, everyone, and thank you for coming to tonight's stream of Universe at Home. I will be the host tonight. My name is Trevor Knuth, and I am a fifth-year astrophysics PhD student. And I will be, I study primarily the sun as well as X-ray detectors. Joining me tonight is my co-host, Sean.
Yep, I'm Sean Bruton. I'm also a graduate student at the University of Minnesota. I'm a second year going into my third year right now, actually, at the end of the summer. And I study what are called high redshift galaxies, which just means galaxies when the universe was very young. So universe was maybe about 1 billion years old, and I'm studying galaxies around that time.
All right. For anyone who is new to the stream tonight, Universe at Home is replacing our usual summer outreach program of Universe in the Park. That was a program in which we would go around to various state parks in Minnesota, and we would present a talk on some space topic, and then we would do star viewing afterward. Obviously, with the COVID-19 pandemic, we aren't able to do that this year, and so we have pivoted to doing these sort of live broadcasting streams about different space talks, so we can still sort of have this outreach and have this opportunity to engage with people about space. Tonight's docket, we'll be going over a 20-minute presentation on the extremes of space. We'll be talking about some of the densest and most massive objects that we know about in the universe, things like black holes and neutron stars. Afterward, we'll be having a Q&A for about 20 minutes. During the presentation, feel free to ask any questions you have in the chat. Sean will be looking through it and making sure that we record all those questions and try to answer as many of them as we can at the end of the talk. After the Q&A, we'll be going to a interactive activity where Sean will be walking through how to create a scale model of the solar system using salt dough, a simple sort of Play-Doh substitute that you can make at home. All right, with that said, let me see if I can get this set up correctly. All right. So, as I said earlier, the topic of tonight is the extremes of space. In this talk, I'm going to first go over physical forces in a nutshell. So when we talk about the extreme objects that exist out in space, oftentimes it involves sort of dealing with these forces of nature at their most extreme. So I want to make sure everyone has a good basis in terms of what those forces are before we get into that. Then I'm going to talk about stars. These are, massive objects that form the center of star systems, and they are sort of the creator of a lot of these sort of extreme objects. Talk about supernovae, the most energetic and largest explosions that we know about in the universe, before going into what is often left behind from these stars and supernovae. Talking about stellar remnants, things like white dwarfs, neutron stars, and black holes, before going into a very special type of black hole called an active galactic nuclei. All right, so physical forces in a nutshell. Physicists have identified 4 fundamental forces or interactions in nature. The first one is one that you are very familiar with, is gravity. Gravity is an attractive force between all massive objects. So it is the thing that keeps the Earth bound together. It is what keeps the Earth orbiting around the sun orbiting around the center of our galaxy. All particles that have mass feel this force. So, every particle within your body is also feeling the mass of every particle in your body. The other sort of large scale force is called electromagnetism. As the name might imply, this is responsible for all electric phenomena, so lightning and the power grid. It's also responsible for magnetism, so the Earth's magnetic field, as well as the magnets you find like a horseshoe magnet. It's also responsible for all light phenomena, so all optics, all rainbows, everything like that. Electromagnetism is also responsible for basically most things in our daily lives. So what we call chemical forces are a extension of the electromagnetic force. These are things like chemical reactions, but also just the structure of a solid is a creation of the electromagnetic force. We also consider electromagnetic force to be the second strongest force, while gravity is actually the weakest of all forces. As sort of an example of how this can be, think about how easy it is for an infant to lift itself up. That's the entire mass of the Earth trying to have the infant on the ground. But just a little bit of chemical potential energy, and the infant can move around pretty easily. Now, both of these forces, gravity and electromagnetism, are what we call forces of infinite scale. That is, that you can have these forces acting on other objects infinitely far away. Currently, the Andromeda Galaxy, a galaxy within the local group but is still extremely far away, is exerting its gravitational pull on everyone on Earth. These other two forces I'm going to go on talking about are very different. They only exist and work at the smallest scales, the nuclear scales. That's why they're called the nuclear forces. The first one is the weak nuclear force. This is the force that's primarily the cause of decay. So things like plutonium and uranium, which are very radioactive and decay very easily, that's a result of the weak nuclear force. But even just more stable isotopes and atoms can decay over time. That is the creation of the weak nuclear force. That is also the third strongest force in nature. And finally, the strongest force in nature is aptly named the strong nuclear force. If you think about it, the nucleus, or the center of an atom, is created from protons and neutrons. And protons are electric particles, all of the same charge. We know that like charges must repel, which means that you have a very, very strong electric repulsive force in the center of a nucleus. However, nuclei don't just rip apart randomly. That's because the strong nuclear force is what binds these nuclei together. So it keeps the center of atoms together and stable. And that's why it's also the strongest force in nature. Now, why I'm talking about these four fundamental forces of nature is because stars are essentially a war between these forces. So you might ask yourself, and I just said about gravity, is why doesn't gravity collapse all things? If you think about it, if you look at a table, all of the particles in that table are trying to pull themselves gravitationally together to a single point, but the table doesn't collapse down. Why is that? Well, the other forces prevent it. Specifically in regards to the table, chemical forces of these structures, or the last structure of solids, will support that table against gravity. Now, when you get to more extreme objects like the stars, chemical forces aren't really able to do the trick because a huge amount of mass means a huge amount of gravity. There's a huge sort of strong pull that wants to make stars collapse down into nothing. So how do we actually have stars support against that? Because stars aren't just collapsing willy-nilly. The sun's been around for 5 billion years. So one is gas pressure provides some of that support. So similar to how a hot air balloon, you heat up the air inside the balloon and it expands the balloon. The sun is extremely hot, and so that supports itself against gravity, but only to a certain degree. Because technically for a star to form, the gravity has to be stronger than the gas pressure within the star due to what's called the Jeans criterion. Luckily, stars also are so hot that particles in the center of stars will slam together with such energy and force to fuse together in a process called nuclear fusion. This is the result of that strong nuclear force I talked about earlier. When this happens, a huge amount of energy is released in the form of gamma radiation. And this nuclear pressure combined with the gas pressure is able to balance the force of gravity for stars. We call this hydrostatic equilibrium, which is just a fancy term of saying everything is equaling itself and it's all stable. So gravity wants to push the star together. Gas pressure, nuclear pressure keeps the star apart. But what happens when that nuclear fuel starts to run out? So the sun, for instance, is currently fusing hydrogen in the core into the element helium. But eventually that helium, all that hydrogen will run out and all you will have is helium in the center. Well, what happens when that occurs is stellar core collapse. Because remember, you're not fueling that nuclear pressure anymore, and so the gravity will start to win out and crush the star down. What happens after that will depend on the star. So a sun-like star, or smaller, such as a red dwarf, these are what we call low-mass stars, or small stars. These stars begin to fuse helium into heavier elements of carbon and oxygen, but they won't be able to go beyond that because they're too low mass. When that happens, a star like the sun will expand to what we call a red giant. And the red giant is an apt name because these stars can get huge. For instance, the sun, about 4 to 5 billion years from now, will expand to the point where its surface is about equal to Earth's orbit or to Mars's orbit. There's some uncertainty as to how big it'll become. It'll become a very massive object in terms of the scope of it. For larger stars, these will fuse beyond carbon and oxygen. They'll fuse heavier and heavier elements up until the point of iron. And when these start to fuse these really heavy elements, the intensity of all this radiation on the inside can cause the outer layers to blow out to extreme portions. So the sun is right here, this little yellow dot. It is, of course, 99.9% of the solar system's mass. It is, far greater than the Earth will ever be. Compared to what used to be the biggest star we know about, VY Canis Majoris, it is this tiny, tiny little speck. So VY Canis Majoris is what we call a red hypergiant. That is to say, we found giants, they were big stars, then we found some bigger stars, like, oh, those are supergiants, and then we found even bigger stars. Okay, well, we had to make up a new term for that. Those are hypergiants. So these are very massive stars that can grow to tremendous sizes. As I said, VY Canis Majoris was the largest star that we used to know about. Now we know the star Stephenson 218, as well as other very large stars. So remembering the sun is this big compared to VY Canis Majoris. Here's VY Canis Majoris compared to Stephenson 218. This is the largest star that I was able to find a positive record on. It is over 2,000 times bigger than the radius of the sun. To put that into perspective, the orbit of Saturn, the sixth planet from the sun, orbits at about 2,000 solar radii. So this star, if you place it inside of our solar system, would expand beyond the orbit of Saturn. That means that it would take, tens of minutes for a signal of light to travel from one side of the star to the other side. And this is a single coherent object. All right, so what about after all this fusion? So as I said before, low mass stars will fuse up to carbon and oxygen, but then they can't go further. So what happens when all of their helium has been fused into carbon and oxygen? Well, low mass stars will create what we call white dwarf stars. So a low mass star can be defined as having fewer than 1.5 solar masses in the core or center of the star. Solar masses is just a unit that astronomers like to use. All it means is 1.5 times the mass of the sun. Now, when a core of a low mass star collapses, it'll get extremely, extremely hot and get extremely dense. But it will eventually reach a point where that second strongest force in the universe, the electromagnetic force, will kind of get into a very extreme state called electron degeneracy pressure. That's the long term. All that basically means is that if you start taking electrons and pushing them together, they reach a point where they don't want to get any further. This is the electron degeneracy pressure. Basically, the electric repulsion of electrons gets so powerful that they kind of hit a barrier. And then once that barrier is hit, we have a white dwarf star. And so this is the ring nebula. At the very center of this nebula, you can see a little white dot. That white dot is the white dwarf star. They are so hot, these white dwarf stars, is that they primarily emit ultraviolet radiation. The sun, a much, much cooler star, primarily emits what we call visible light, and this is much more energetic than that. They're called white dwarf stars because they're so hot they will appear white to the naked eye. And finally, when these stars are created, they're around the size of Earth. So imagine taking a mass about the amount of the sun and crunching it down to the size of Earth. That is how dense these things are. And because low mass stars stop fusing around carbon and a little bit of oxygen, it essentially makes them giant white hot diamonds the size of planets. That's why I call them planet-sized diamonds. The outer layer of the star, the stuff that doesn't go into the core of the white dwarf, actually gets pushed out by all of this radiation pressure coming from that white dwarf as it emits UV radiation. And that's what these colorful layers are on the outside here. These get lit up by the radiation from the white dwarf star, and they get really bright and colorful, and we call these planetary nebula, which is a bit of a misnomer as there's nothing planetary about them in sort of the way that we understand planets. All right, so that is low mass stars. What happens to the bigger ones? High mass stars, when they reach the end of their fusion lifetime, which happens around fusing iron and a little bit of nickel, they go into a full core collapse that creates what's called a supernova. Supernovae are explosions of cosmic proportions. This supernova, 1994D, is visible right here. Compared to this galaxy, you can see the supernova is actually brighter than the galaxy, and that's not atypical. Supernovae tend to be brighter than the entire galaxy combined because of how energetic and bright these objects are. The explosions are so hot that they'll actually fuse elements heavier than iron. So things like silver and gold will get created within supernovae. And now as astrophysics has gotten further along, we've come to understand other processes which create the even heavier elements. Some of these supernovae, because they are so bright or even visible during the day, they'll actually look like a star that you can see in the middle of a bright sunny day, just to sort of show how bright these become. Here on the left is the remnant of a supernova viewed by Tycho Brahe, an astronomer of hundreds of years ago. And on the right is the supernova remnant of Johann Kepler, another famous astronomer. What you're seeing here is X-ray radiation from these. The visible, so what we can see, we won't be able to see anything here. That's because this gas, well now plasma, is so hot and sort of spread out that it primarily emits X-ray radiation. It doesn't really emit visible light. All right, so when these supernova go off, what do they actually leave behind in the center? So when you have a mass of a star core, which is greater than that 1.5 times mass of the sun, but less than 3 to 5 solar masses, you create what's called a neutron star. Basically, the electromagnetic force, that second strongest force in nature, isn't strong enough to overcome 1.5 solar masses of material crunching down onto it. This causes the electrons to crash into the nuclei, the center of the atoms, and combine with the protons and create neutrons in a very, very energetic process. The energy released from this process is believed to be a major source of the energy of the supernova. What you're left with at this point is a dense ball of pure neutron matter. We call this neutron degeneracy pressure. So instead of the electromagnetic force supporting the star against gravity, you now have the strong nuclear force, that strongest force in nature. So now we are looking at the absolute extreme end of forces that could support matter. Now, neutron stars are a whole different ballpark from white dwarfs. So as I said before, a white dwarf, you might have a 1 solar mass white dwarf star compared to a planet like Earth. A neutron star can be 3 solar masses in the size of a large city. So here we have a artist rendering of a neutron star sort of dangerously sitting above the city of Vancouver. This kind of shows you that 20 kilometers is a typical size of neutron star. They are just so extremely dense. If you picked up a small teaspoon of neutron star matter, it would weigh as much as a mountain. If you had a handful of neutron star matter, you'd be holding essentially the entire mass of the Rocky Mountain range. So these are extreme objects. Another interesting thing about neutron stars is there are special versions of them called pulsars. So when a neutron star is formed and that core collapses, it can become highly magnetized. And it can also be spinning very, very rapidly. This creates a interesting dynamo, which will release these highly beamed jets of radiation. Here we have the Vela pulsar or Vera pulsar in the X-ray. What you're seeing is this beams of radiation are sort of hitting all of this diffuse gas around the neutron star, making it light up in X-ray radiation. These objects are called pulsars because these beams of radiation coming out either side, similar to kind of how a lighthouse will function, will sweep around in a giant circle. And as the beam goes by you, you'll see the star pulse. And it'll pulse once per rotation as the beam goes by you. Thus, they were called pulsars. Now, an interesting thing about pulsars is each pulsar will kind of have its own characteristic frequency. That is to say, it'll pulse at the same rate as it always does. And if you know the positions of pulsars and their frequencies, if you take a spacecraft and you go through the galaxy, you can use your X-ray telescopes to find these pulsars, know where they are, and figure out where you are in the galaxy. So these can essentially create a galactic-sized GPS network for navigating through galaxy. And this is actually a topic that is being studied and researched at the University of Minnesota, how to use pulsars for space navigation. All right. So I gave an upper limit of about 3 to 5 solar masses for neutron stars. But what happens if you keep adding on more mass? What if the gravity becomes just too much for even the strong nuclear force to hold it up? When that happens, there's nothing left to stop gravity, at least nothing that we know of. In this instance, matter will collapse in on itself entirely and create what we call a black hole, the densest, most extreme sort of object that we have ever sort of encountered. The gravity of a black hole is so powerful because it is so dense that light itself cannot escape past a special boundary. We call this boundary the event horizon. And so if you ever see an artist's interpretation of a black hole, the black circle is actually the event horizon. The black hole itself exists as a singularity, a infinitely small little point at the very center of this event horizon, where all the mass is concentrated. There is a quip in astrophysics that black holes have no hair. That means that they're only defined by mass, so how much material went into that black hole, charge, so black holes can have electric charge, although in nature we don't believe any really do, and finally spin. Black holes can be spinning. And because of the fact that charge doesn't really exist in black holes in nature, they only use 2 properties, mass and spin. Gravity has kind of stripped away every other distinguishing characteristic of black holes. All right, so supermassive black holes. How big is big? So we know that black holes are created from stars are about 3 to 10 solar masses. That is to say, not much bigger than stars themselves necessarily. However, we know of black holes that can go from tens to hundreds of solar masses, much larger than sort of what you find at the end of a supernova. These are called intermediate mass black holes and believe that they're created from remnant mergers. So taking multiple neutron stars or black holes, slamming them together and creating a bigger black hole. However, we also know black holes are millions to billions of solar masses. So how are these actually created? Well, we now have in this day and age pictures of these supermassive black holes. So this is the Event Horizon Telescope image of M87's supermassive black hole. M87 is a galaxy that is some distance away. And what we're seeing here is the radiation coming from around the black hole. This was created, I believe, within the last couple of years, and then all the data was sort of processed together to produce this image. And what you're seeing is the actual event horizon of this black hole at the center here. So supermassive black holes, what are they? How are they here? What do they do? So first of all, I call them galactic anchors because we believe that every galaxy has a supermassive black hole at the center. Milky Way is no different. We have a supermassive black hole that we call Sagittarius A star. It's about 4 million solar masses. And this picture here on the right is a graphic created by the UCLA Galactic Center group. They're a group that monitors sort of the rotation of stars and objects near the center of our galaxy. This yellow star here is Sagittarius A star. It is a black hole that you can't see directly. And so instead you're observing all of the orbits follow these stars as they kind of get whipped around this extremely large object. Now, 4 million solar masses is pretty big, but it's not the biggest by any stretch of the imagination. There is a black hole called TON 618, a great name for a supermassive black hole. And it is the most massive black hole that we know of. It is 66 billion solar masses. So 66 billion suns have to combine together to create a black hole of this size. The event horizon, so the barrier around this black hole from which not even light can escape, is at 198 billion kilometers. To put that into perspective, that is 1,323 AU, or astronomical units, and AU is a distance from the Earth to the Sun on average. Pluto, the most distant sort of dwarf planet in our solar system, is 39.5 AU. So you could take the entire solar system, throw it into this black hole, and it wouldn't even know what had happened. That's how sort of large and massive this object is. Now, an interesting thing about these black holes is that we don't really know necessarily how they form. So oftentimes, supermassive black holes, at least in the past, would consume vast quantities of gas, dust, and stars. Basically, they would just sweep up all this material. As the material got closer to the black hole, it would become superheated, hotter and hotter. And then twisting magnetic fields would also form in this sort of swirling disk of dust and gas. And eventually, you start to have these giant beams of energy and plasma get thrown out from either side of these black holes. So because these black holes sit at the center of galaxies, they're kind of like galactic nuclei. And not all galactic nuclei are emitting these jets. For instance, Sagittarius A star is not. So we call these active galactic nuclei. And here we have a picture of a galaxy with an AGN in the middle, shooting out giant beams of energy. Now, when I say giant, I do mean giant. I have in the text here galaxy-sized beams. Most galaxies are on the order of 100,000 to maybe 1 million light years across. And then these jets can actually become 1 million light years in length. So a singular beam of energy traveling 1 million light years out into the cosmic space. These are truly, truly huge things. All right, now a quick summary of all of this. So stars are a constant battle between gravity wanting to push inward and collapse a star and other forces trying to push outward. Those outward forces can be things like gas pressure, nuclear radiation, electron degeneracy pressure from that electromagnetic force, neutron degeneracy pressure from that strong nuclear force. Stars, as they reach the ends of their lives, transform into giants, supergiants, and hypergiants due to the fact that the core continues to collapse as it runs out of fuel and fueling heavier things and pushing the outer layers of the star outward. Small stars, when they collapse, will create planetary nebula and white dwarf stars. These are planet-sized star remnants that can have as much as 1.5 times the mass of the sun. They're primarily made of carbon and oxygen. Larger stars will detonate in massive explosions called supernovae. Explosions are so bright they can outshine an entire galaxy. These supernovae leave behind neutron stars and black holes. Supermassive black holes exist at the center of galaxies. Some are actively consuming amounts of matter, then emit out these huge jets of energy and are called active galactic nuclei. We believe that in the present day, so galaxies near us don't have AGN because all the material that was available to be sucked up and created by these supermassive black holes has been. So we believe AGN are only existing in the past. All right, thank you for watching. We'll be taking any questions you have. Questions that relate to the presentation are, of course, welcome, but anything that is related to space, academia, astrophysics, science in general, we'll be happy to take. Thank you.
Okay, so we picked up a few questions during the presentation, so I'll start with those two. First, we have Ashwath, who wants to know, can a small mass have large gravity?
All right, interesting question. So as far as we know, no. The amount of gravity that an object has is directly proportional to the mass that it has. And so you can have a spatially small object have a lot of gravity, like a black hole, but unless you have a lot of mass going into that, then you won't be able to have a strong gravitational pull. Um, Unless we could somehow interact with a gravitational force in some other indirect mean, there's no way really around that.
I think that's a good answer. The next question is from Raja, and he would like to know, are black holes 2D within a 3D plane or space?
Right, so that's an interesting question as it deals with spatial geometry of sort of black holes and space itself. Um, as much as we can understand black holes, uh, the event horizon is definitely a three-dimensional object. It has a spatial scale. What is going on with the black hole itself, that is to say, the singularity in the middle, there's not much that we can say. Calling it a singularity is kind of a math model. We're describing it with a math stand-in that seems to work, but that is all it is, sort of a stand-in. It's an approximation. The reality of what goes on inside a black hole is something that, is very difficult to figure out because we can't actually observe it. So is a black hole itself, that point at the middle, a 2D object, a 1D object, a 3D object? That's up to a lot of different interpretations.
Okay, next we have Mr. Fizzer, who would like to know, does antimatter have negative gravity?
Right, so antimatter does not have negative gravity. Antimatter, for anyone who doesn't know, is essentially a bizarre, exotic form of matter, which, when it touches matter, will annihilate and create a huge amount of energy. It only really gets created in sort of extreme particle interactions, like what you have at the Large Hadron Collider in Europe. What we understand about antimatter is that if you had a universe entirely created of antimatter, it would look pretty much the exact same as our own universe. So it would still have positive gravity. You have antimatter planets orbiting around antimatter stars, just like normal.
Right. I would add to that, there was an experiment semi-recently, I think it was within the last 2 years or so, that was able to synthesize basically anti-hydrogen. It took the antiparticles that make up hydrogen and was able to build an anti-hydrogen atom. And it had the exact same spectral fingerprint as regular hydrogen. So as far as we can tell, the electromagnetic interaction behaves very similarly as well. Just kind of opposite charges and everything else the same. Next question is from John Strobel, who asks, can you clarify why AGN only exist in the past?
Yeah, of course. So if we go back a couple billions of years, the center of galaxies, you have a lot of dust and gas and stars, and you have a supermassive black hole sitting there. The dust and gas near supermassive black hole will sort of decay in its orbit due to gravitational radiation, and it will fall inward. And eventually, all of the dust and gas and stars and anything that was near the black hole that the black hole will suck up, it has sucked up. So essentially, over time, you can think of, a cloud of dust around the black hole, goes into the black hole, and there's simply no more dust for the black hole to uh, absorb anymore. Because of that, you don't have anything to power the AGN. And so in the present day, so the Milky Way galaxy, the Andromeda galaxy, despite them having supermassive black holes, they're no longer active galactic nuclei.
All right, next question is a fun one. Nick Carter would like to know, what space movie is your favorite, and which do you think depicts black holes most accurately?
All right. My favorite space movie might be The Martian, just because of its strict accuracy to space and science. Besides the one major error that the author has said he understands is an error, and that is the storm at the beginning that causes the whole thing. The most powerful storm on Mars will feel like a very, very gentle breeze on Earth because there's no atmosphere, basically. In terms of the most accurately depicted black hole movie, I think it has to go to the film Interstellar. Which everyone has seen Interstellar. It has a black hole that is sort of features very prominently within the story. And not only that, but the physical effects of black holes are also very accurately portrayed in that film with things such as time dilation. I believe the money that went into visualizing that black hole even led to some papers being published.
Right, I've heard that as well. And then Trevor's favorite movie is The Martian. My favorite space movie is probably Interstellar. I really enjoy that one. The like Trevor said, the physics around the black hole is really quite accurate to a large extent. Without getting into spoilers, there's one point where they do a scene inside of the black hole that is definitely taking some creative liberties, I would say.
Right. Once you go inside the black hole, our bets are off, but probably not what happens in that film.
Okay, we got one more question that just came in. Sumonic would like to know, when you say dust, do you mean solid silica?
So astronomers kind of get funny with their definitions. For instance, any element heavier than helium, we just call a metal, which means that carbon and oxygen are metals to astronomers. Um, when we say dust, we mean specifically, it can be silicon, but it can be any sort of crystalline structure particle that is floating out in space. Um, Yeah, I mean, I guess it's just a lot of times for astronomers, dust is stuff that gets in the way of what you're trying to look at. But some people really like to study the dust. But yeah, not specifically silica, but it can be.
One other thing, there's no other questions, so I'll just jump in real quick. One other thing that's important about dust is the scale of it. It's much, much larger than the other things that you're going to be dealing with in space usually. If you're looking at gas or ionized gas or anything like that, you're dealing with atoms or protons or electrons, which are, some of the smallest particles in the universe. We're looking at nanometer scales and things like this, angstroms. If you're looking at dust, you're talking about stuff that's more like a micron, which is going to be about 4 orders of magnitude larger at least. Okay, another question about movies. Raja would like to know, which space movie has depicted space the worst?
Oh dear. Armageddon was pretty terrible.
Yeah, Armageddon. I don't know how much of a urban myth this is, but supposedly, whenever NASA was doing technical interviews with potential hires, they would have them watch Armageddon and write down all of the physical mistakes that they've made, all the mess ups with physics, and people would usually get into the 80s or hundreds or something like that.
Yeah. Also know the film Gravity, starring Clint Eastwood, not Clint Eastwood,
George Clooney.
George Clooney and Sandra Bullock also has some incorrect orbital physics in how things are happening. But that's a more recent example than Armageddon. And I'm sure there are many, many space movies have bad physics going on.
Definitely. All right. Another question. This one's from Kurt. He asks, do black holes ever become anything else? Or is a black hole a kind of end state?
So black holes will never transform into something else. There is a hypothetical way in which black holes evaporate. It's called Hawking radiation. It's named after Stephen Hawking, the famous physicist. And basically, black holes, it's a mechanism in which they can slowly radiate energy, but it's such a slow process that it will take, I don't even know the number, 10 to the 50, 10 to the 100 years before these black holes will actually disappear. But all they'll do is disappear back into energy. They won't become like a new object, rather.
All right. We got a question from Nick. He asks, do black holes really move around while destroying anything that comes into their gravitational pull?
So black holes can move around. They can form within, say, a star cluster and then get kind of flung out and then sort of travel through space. But the way that a black hole moves is the way that a planet or a star would move. And so they aren't really rogue objects kind of, traveling around. They tend to stay in the orbits of the star that created them. That being said, if a black hole is traveling through space and it does come upon something else that gets into its gravitational well, it will consume it and it won't really know it happened unless it was another black hole of similar size. That creates a really interesting phenomenon where these two black holes or neutron stars will sort of spiral inward and kind of wring out gravitational energy in the form of gravitational waves. We can actually observe that with observatories like LIGO, of which we had people here at the University of Minnesota a part of, the LIGO collaboration. And that was a really big sort of observation that happened 3, maybe 4 years ago, and it sort of opened up a new branch of astronomy. All right. Looks like we're running out of time for the Q&A, so we'll be moving on to the next portion. Thank you, everyone, for those questions. They were really great. Now we'll be turning it over to Sean to go through how to create your own solar system model.
Right. So let me make sure that this camera looks decent. All right. So we sent out instructions through the email list this morning on how to make salt dough. Salt dough is basically just make at home Play-Doh. So it looks like you won't be able to see my head during this, unfortunately, which means that my chef hat that I prepared is for naught, but I'll put it there as a reminder. But so I have here 3 pounds of salt dough. It's just kind of like Play-Doh. And how this is going to go is there's a sort of formula sheet on this page of NASA's sort of do at home lessons. It's going to be page, I'm posting it right now. Let's see, page 33. There we go. And so what we're going to be doing is splitting this up into tenths over and over again. And some of the tenths will go into making planets. Some of the tenths will get split again. And in the end, we'll have a scale model of the solar system. And you might be surprised at just how much mass, or radius rather, is going into the large planets. It's important to note here that the mass that we have here is not going to be representing mass in our model, but volume. So this is essentially all the volume in the solar system. So we'll start out, and step 1 says to divide the clay into 10 equal parts tenths. So I have this dough cutter, which is nice, but a pizza cutter would work as well. The best way I found to do this is just make a cut right down the middle, and then you're going to look at a third for half of the remaining dough. Take half of it, look at a third, estimate just over a third and make a cut, and then follow that line through. Cut that smaller slice in half, and that's going to give you approximately 36 degrees on these slices. And then with the remaining bit over here, we're going to cut it into thirds. So that's the sort of technique. And then you always just want to follow these lines through. And then you'll have 10 slices. And so we're going to use 6/10 right off the bat of our total dough to make Jupiter. So we've got Jupiter over here, plop down 6 pieces of dough. Then we're going to use 3/10 to make the beginning of Saturn. Saturn will actually pick up a little bit more dough as we go along, but this is the start of the Saturn radii. And then this little bit of dough that we have left to work with is what's going to get partitioned out. Some of it to Saturn, some of it to the rest of the planets. We'll see where it goes. So you're going to do the same technique again. We're looking for tenths on this dough. So we'll just make our same cuts and the same technique that we had before. There's 10 right there. And it says we want to add 5/10 to Saturn. So half of that, half of the remaining dough, go into Saturn again. Going to use 2/10 to make Neptune, and then 2/10 to make Uranus, and the remaining clay, 1/10 of this, let's do there, to go into the rest of the stuff. Flatten it out again. Same technique, tenths again. It starts to get a little more difficult as you get smaller and smaller. This remaining clay gets divided into fourths. So we have fourths here now, and we're going to put 3/4 into Saturn, and then 1/4 gets to stick around to go into the rest of the planets. There's 3/4 going there. We are now down to quite a small amount of dough. And this is, we haven't even started building Mercury, Venus, Earth, Mars, or Pluto is included in this as well. All right, we're splitting it again into tenths. And we're finally going to start on Earth and Venus. Boom. We'll cut there, cut there, cut there, and a cut there. 2/10 to make Earth, 2/10 to Venus. Starts to get a little difficult to even get it off your fingers when it gets this small. There's our little Earth. Venus is a little smudge. And then 4/10 are going to Uranus, which is about that much. And then the remaining clay, the 2/10 left, is going into step 5, which we're going to split into tenths again. So since this talk was about the extremes of the universe, I thought while we were doing a solar system model, it makes sense to talk about the extremes of the solar system. So though we haven't really gotten to Mercury, building it quite yet, the most extreme thing or one of the most extreme things about Mercury is that it's the fastest planet. It's actually how it got its name. Mercury was the Greek messenger god. And so since he was whipping around the sun, people noticed this planet was moving really quickly across the sky and would named it appropriately for the fastest Greek god. Okay, so we've got little tenths here again. We're going to add a 10th to Mars, the littlest, tiniest little thing. And then 4/10 to Neptune, 4/10 to Uranus. Coming off my fingers. And then we're splitting this remaining part into tenths again, and then we're finally gonna make Mercury. And I think we'll stop there in the interest of time. So we'll continue on talking about the rest of the extremes of the solar system. Venus is going to be the hottest planet, actually. You might expect that Mercury would be the hottest planet, given it's the closest one to the sun. But actually, Venus's extreme atmosphere has basically a runaway greenhouse effect. And that is going to make it so that its temperature is about 900 degrees Fahrenheit. So it's hot enough that we've only landed maybe one probe, at most a few probes, but the one I'm thinking of in particular is this USSR probe landed on the surface and was finally able to get our first picture of Mercury. It was made entirely of metal, and it lasted all of about an hour before it just completely melted and became one with Venus. So we've got Mercury here, and it is just incredibly tiny. The remainder of this stuff that we would divide up, 2/10 is going to go into Uranus to give it a little bit more mass, and then 9/10 of the remaining goes to Mercury, and then 1/10 would go to Pluto. So I mean, we're down to crumbs at this point. I can't even hardly keep track of it. But so let's form these up a little bit so that we can kind of get a better sense of what size we're dealing with. Jupiter and Saturn especially are obviously just taking up the vast majority of the volume here. So continuing on our little tour, Earth is actually the densest planet, which is kind of a surprising one as well. Comes out to about 5.5 grams per centimeter cube, which, to give you a sense of scale, if you're not familiar with units of this, water is 1 gram per centimeter cube by definition. So it's 5.5 times as dense as water on average. So it's going to be much denser in the middle, but this is just an average that we can work with. In comparison, on the opposite end of the spectrum, Saturn is going to be about 0.8 grams per centimeter cube. It's lighter, it's less dense than water, which means, very coolly, if you were to get a giant bathtub somehow and fill it up with water and drop the planet Saturn into it, Saturn would actually float in that bathtub, if you ignore the fact that it's gas and confusing things like that would make for strange physics. Jupiter, as we can see here, I'll actually just pull in the camera so we can get a closer look at some of these. Jupiter is clearly just dominating all the volume here. The volume of Jupiter is obviously making up about 6/10 total of the planetary volume, but its mass is also 318 times Earth's mass. So it's just taking up, as well as most of the volume, actually about 70% of the total mass in the planetary bodies in the solar system. So we've hit Saturn. We haven't hit Mars. What is there interesting on Mars? Mars, we've sent the most rovers to Mars. We actually had the most missions to Mars out of any planet in the solar system. Uranus is going to be sort of, I couldn't really find anything that was the most extreme about it, but it does actually have a ring system. It's just that it's so faint you usually can't make it out. And then it's also very hard to pick out through your sort of standard telescope because you can't see it by eye. But it's going to orbit on its side. So, or not orbit, rotate on its side. So it spins sideways compared to the rest of the planet. It's also probably the planet in terms of extremes. I guess it's the planet that people make the most jokes about. That's one thing it's got going for it. That leaves us with Neptune and Pluto. So Neptune is the coldest planet. It actually does follow what you'd expect since it's so far away from the sun. It's going to be sitting at about like, I think it was like 80 Kelvin. It's negative 360-ish Fahrenheit. So, I mean, it's pretty brisk, but they always say it's the wind that gets you. The wind on Neptune is about 10 times that of a Category 5 hurricane. So the wind chill is probably pretty brutal there as well. And Pluto, what is Pluto most extreme at? Pluto is the planet that's been voted out of being a planet the most at once. So that's my tour of the extremes of the solar system. And as we can see, we've just, let's compare Mercury to Jupiter, and then all the rest when we got Venus, Earth, and Mars. And then on the scale, you may be asking yourself, okay, well, we didn't do anything with the sun. And that's because I don't have enough flour in my kitchen to make the sun. The sun on this scale would be rather large. The thing that I could find that was closest to it, it needs a diameter of about a meter across. So the closest thing in my apartment I could find was our giant beanbag chair, which is about a meter across. So that's where the sun would fit into our model here. So that's the quick and dirty way to build a salt dough solar system model, where you end up with some nice little spheres. If you add food coloring to them, you can make them all nice and colored. And then actually for most of these, you can toss them in the oven for 10 minutes, bake them, and then they'll harden up. And then you could play with them, use them as little marbles, set them up into proper distances would be a fun thing as well. And that about wraps up my quick and dirty salt dough tour. So if anyone has any questions, let me know.
All right. Thank you, Sean. Yeah, we actually have a few more minutes. So if anybody does have any questions, either about extremes of the solar system, building the model, or any other questions about space and astrophysics, feel free to ask them. Also, give a plug for next week's Universe at Home is going to be Asteroid Adventures and Majestic Meteors. It'll be presented by Lauren Loftman. The topic would be, what are meteor showers? Have you ever visited an asteroid in space? Are we in danger from all those big rocks out there? Find out these answers and more next week. All right, looks like we have a question for you, Sean, from Abdullah. What is your favorite planet?
That's tough. I'm kind of partial to Earth. It's got nice weather, I'd say. Usually, not in the winter up here in Minnesota, I guess, but generally. It's also got a lot of people I like. Although Mars is giving it a run for its money. Mars is pretty cool.
I'm always partial to Jupiter, because Jupiter is the most active in terms of like the magnetic field around Jupiter.
Right.
And all of its moons are really cool, like Europa and Io. Looks like we have a question about the model. Did Saturn include its rings within the volume?
No, this one does not include Saturn's rings for measuring what we've done here essentially is just taken the total volume, and that's only going to be measured to the planet's surface. And so it's not going to include the rings in the volume that we've dished up. Although my first thought on that would be that it would make Saturn slightly larger than it is because it's going to be a little bit more volume in the rings themselves, but like really minuscule in comparison to the planet itself. And it would really just make Saturn dominate over these smaller planets even more if we were to include it.
So we have a question of, are there people in Jupiter? No, there are not, but there is a liquid hydrogen core inside of Jupiter, which is interesting. There is basically far more Earth-like material in Jupiter than there is on Earth. So there's a lot of iron, there is a lot of gold, a lot of anything basically inside of Jupiter. It's just that it kind of has an atmosphere that is by far the majority of its mass, but it does have this sort of really dense liquid metallic core swirling around the inside. All right, so we have a question from Ashwath saying, what's your thoughts on extraterrestrial life? Sean, I'll let you go first on this.
Sure. So this is one that you can get answers all across the board. In my opinion, with 100 trillion galaxies, and then galaxies being made up of 100 billion stars, and then from what we found from recent missions, we've actually been able to quantify how many exoplanets there might be, and it looks like most stars have some kind of planetary system. When you start dealing with that many planets, it's really just a numbers game. It's saying, this is all to say, I think that it would be extremely unlikely for us to be the only life in the universe. But in terms of actually bumping into that life, that's an entirely different question, and one that actually gets a lot more difficult to answer. You have to ask yourself, how long do civilizations last? Are they going to be able to last millions of years? How far across their galaxy are they going to be able to colonize? What are the odds of there being another civilization in our galaxy? And how far might we expect them to spread out? Would we ever bump into them? That's a much more difficult question to sort of start to quantify. Not to say that the question of whether does life exist at all is an easy question.
And I personally think you could probably find extraterrestrial life closer than we think. So there is a planet around Jupiter called Europa, which is believed to be entirely covered by a thick ice crust, and beneath that crust is an ocean that astrophysicists believe has more water than the entirety of Earth's oceans. And Europa gets constantly heated by the gravity of Jupiter. So what we call tidal forces, the same tidal forces that create, the tides on Earth from the moon. Jupiter's tidal forces create heat inside of Europa. And so you have this sort of molten core releasing energy into this, sub-ice ocean. And given enough time, I think it's certainly possible that microbial life could have formed within those sort of volcanic sea vents, and that if we ever go to Europa and dig under the ice, we may find, little cells floating around in the water.
There is a proposed mission very, very far down in the pipeline, hasn't gotten very far in terms of development with NASA to essentially make a submarine that would land on Europa and then just melt its way through the ice until it gets to the subsurface ocean and then be able to explore around the ocean. I believe there's more information on that one online. I don't know what it's designated as right now.
I've heard sporadically about this mission over years, and I hope it eventually happens, but all right, looks like that is all the time that we have. Thank you everyone for coming to Universe at Home tonight. Once again, you can come again next week, same time. We'll be learning about asteroid adventures and majestic meteors, and we'll have one more event after that, which will be a wild card, talking about the current events happening in astronomy. So once again, thank you all, and hopefully we'll see you next week.
Yeah, thanks everyone.